So let's look at problem 20.5, which is a really good example of what chapter 20 is about. It's a classic example. Ones like this can be on the final, where something's varying as a sinusoidal function of time. You got to figure out, first you got to write the function. Like 20.3 and 20.4, they tell you the function. This one, they don't. We got to figure out the function, and then we got to solve it to figure out some different things. Okay, so it's like one step harder than 20.3 and 20.4, so which is why I chose it. Okay, so the temperature in Gavin's oven is a sinusoidal function of time. Gavin sets his oven so it has a maximum temperature of 300 degrees and a minimum temperature of 240. Now, most of our ovens, we don't set that, right? We say, okay, we want to bake at 300 degrees. We set it to 300, but he's got a fancy oven that he can say, I want it to go up to 300 and down to 240. So once temperature hits 300, it takes 20 minutes before it's in 300 again. Okay, so we know it goes up between 300 and 240. So it goes 300 is the highest and 240 is the lowest, and it goes back and forth between 300 and 240. Now, all ovens work that way. If you set your oven at 300, it doesn't stay 300 all the time. Instead, the element comes on, heats it up to maybe 310, shuts off when it gets to 310, goes down to 290, and then the oven says, oh, it's 290, better turn on again, goes back up to 310, shuts off, goes back down to 290. So everybody has a sinusoidal oven. It just, we don't get to set the bottom temperature. It's built into the oven. And I don't know what they do. You don't want to have it like 1 degree around 300 because then it'll be constantly shutting off, shutting off, shutting off. The element will get hot, get cold, get hot, get cold. And that can be really hard on the electrical systems and be hard on the elements. Maybe it's not hard on a heating element for an oven. I know it's hard like in your house if you have a heat pump or something. If you set your temperature at 70 degrees, what typically happens is the heater comes on and maybe goes to 72, shuts off, it lets it go down to 68, shuts on, it turns on again, goes to 72. So basically, if you have a heater like that, you have a sinusoidal heater. You don't want it to be too close because it can be hard on the equipment to constantly be shutting off and shutting on. It wants to wait a little while, so it doesn't have to do it that often. Same as a refrigerator. You set your refrigerator 40 degrees. It doesn't always stay at 40 degrees. The temperature, maybe the refrigerator comes on and turns it down to 38, shuts off, it goes up to 42, turns on again. Because again, I know it's really hard on refrigerators to be constantly turning off and on again for the compressors. So it's sinusoidal. So this is a typical oven, except his is a fancy oven. He gets to set what the bottom one is. Most of us is built into the whoever designed the oven, they decided for us. Okay, that was a long-winded thing about stuff. But hey, good stuff, right? This is real world stuff here we're talking. All right, now Gavin's cake needs to be oven for 30 minutes. Oh, they tell us the period is 20 minutes. They say once temperature hits 300, it takes 20 minutes before it goes to 300 again. So our wave looks like this. So between peaks, between 300, it's 20 minutes. And that means that's the period. Between peaks, between troughs, that's the period. So we know the period. And we're going to use, looks like minutes for time. Okay, we're going to use time in minutes because it makes sense. So then he says, they say Gavin's cake needs to be in the oven for 30 minutes at temperatures at or above 280 degrees. 30 minutes above 280 degrees. So it's got to be in there for 30 minutes, has to be greater than 280 degrees for it to cook. A lot of the time it's below that, right? Most of the time, because 280 is closer to 300. So we want to have 30 minutes above that. And he puts the cake in the oven when it is at 270 degrees and rising. So he puts it in when it's at 270 and going up. Now, 270 is exactly halfway in between. I think that will help us figure that out. But so he puts it in at 270 when it's exactly halfway in between. Okay, that's all our information and rising. Okay, now we need to draw our picture, which will help us figure out the function. So we draw the picture. So we're going to call, okay, first off, I don't need to have anything below 0 because we're going from 240 to 300. And a good trick to use is we will skip. We're not going to start at 0. There's no point. So let's just say, okay, here's 240 and here's 300. You know, we don't need to show all the way where 0 is because we don't care about that part of it. So putting this axis like this here is just nice so we can put the time there. Okay, so we don't need to go to 0. That would be like, we'd have to work way up here and put the 0 down there. Okay, so that's one trick. Now, we put our lines here, our dashed lines. And we need to have 30 minutes above 280. So we're going to need a whole bunch of cycles, right? Because we got to be above 280. So 270 is in the middle. So let's put our 280 in. That's 1/3 of the way. So 280 is right there. So we got to be above 280 for 30 minutes. So we might need a lot of waves in here. And it waves every 20 minutes. So let's say this time 0, it should always start at 0. So let's say this is 20, because we want to get a lot of waves in here. There's another wave, another wave. I don't know how many. I haven't looked at the answer or anything. So, and that's really bad. My thing goes down there. Okay, I'm going to do a bit more carefully now. More carefully with this. Okay, let's make it a straighter line. Okay, 20. Oops, what am I doing? 40. Okay, 40, 60, 80. Hopefully we don't have to go past 80. That'd be 4 periods. Right? 1 wave, 2 waves, 3 waves, 4 waves. And I can put the dashed line. The middle is right here. Now I'm going to put a different color. Where's my blue? Ah, here's a blue pen. Okay, now where does the wave start? The wave is at 270. He puts it in when the wave is at 270, right? And going up. So at time 0, the wave is right there at 270 and going up. Which is really nice. That's exactly in the middle. Whoa, wait. Oh, this is too easy. That then the phase we know is going to be 0 because it starts right where sine wave should start. Oh man, I was hoping to make it hard to find the phase. Okay, our phase here is going to be 0 because it's exactly in the middle and going up. So that's where sine wave should start, exactly in the middle and going, oh, this is no fun. Okay, then at 20, it does the same thing again. So same thing again, same thing again. Halfway in between at 10, we know it's going to hit the bottom. So we put those points in. At 5 minutes, it's going to be up here. It's going up. So halfway in between those, halfway in between those. So that's 5. So that's 5, 10, 15. Oh, this is really easy. Oh, that's too bad. Oh, well, whatever. So 5. So now we can draw a wave. It looks like this. And I actually want to keep going. So I'm going to put one there, put one there, put one there, put one there. So it goes up like this. There. Again, I don't know how many I'm going to need. Hopefully not that many. Okay, now what we want is how long? 30 minutes greater than 280. So there's 280. So we want it to be 30 minutes greater than 280. So we need to figure out, let's see, according to my picture, this is 10 minutes, right? Yeah, 10 minutes there. So that time there looks like it might be like, I don't know, 8 minutes, right? Between the 2 green dots. So it's going to be like roughly 8 minutes. I'm above 280, so this one would be 8 minutes. And notice my sine wave, that one's skinny and that one's fat, but oh well. So another 8 minutes, another 8 minutes, another 8 minutes. I'm just guessing about the 8 minutes. That's what we're going to have to figure out. That's the hard part of this problem. So 8, 8, 8, 8. That would be 32. So maybe 4 waves is enough. I might have to go 5 waves. I don't know. But we get the idea, right? So we need to figure out now how long between each wave. So we got to figure out those points, and that's the whole part of this problem. That's where we got to figure out the inverse sign and figure out both the symmetry solution, the principal solution, all that stuff we talked about in class. So now the hard part, we figure that out. Okay, first we got to write the wave. So we can say that the time, the temperature, we're going to solve for temperature, so I'll make it a capital T. The temperature in the oven, the amplitude is 30, right? It goes 30 up from the middle and 30 down. So it is 30 sine 2 pi, the period is 20. We're going to use minutes because it makes sense because they tell us minutes. So 2 pi over 20. times x minus, and the phase is 0. It starts exactly where sine wave is supposed to start, right in the middle and going up. I wish they'd said, okay, let's pretend. Let's say they started, he put it in 10 minutes after, or let's say he put it in, yeah, if you say put it in 10 minutes after his timer started, then our phase would be 10, and it would start over here going up, right? And then our phase would be 10. But so that's always where it starts going up. And here we just know it starts going up at 0, so x minus 0. So I don't need to put that, but I'm going to just for the sake of it. And the average is 270. It goes up and down past 270. So there's our sine wave. We want to know when the temperature is 280, so we can figure out both those points and subtract them and figure out how much time we get for each wave in the oven. Okay, so we want to set this equal to 280. Okay, now it's algebra time. I'm probably going to have to erase a bunch of stuff to figure all this out on the board here since I've filled out the board with a picture. But I'll do as much algebra as I can here right now and figure out, okay, first we take the 270 away from the 280. That gives us 10. And I'm going to do this, so that gives us 10. And then I'm going to divide it by 30. So what I have left now is sine of 2, and also really that's 0, so I can just write it like this. Oh, that's also 1/10. 2 over 20 is 10. So it's pi x on the top divided by 10. Sine of pi x, yep, because 2 over 20 is 1 over 10. Pi x over 10, 0 goes away, so we don't have to worry about that. Yep, that's right. Equals, I'm going to put the 30 over here. So I had 10 divided by 30, so that's 1/3. And I'm doing a lot in my head right now, but that's pretty easy to do because I'm running out of room. Don't do what I do, okay? Show all your work. But 270 minus 280 minus 270 is 10. 1030 in the bottom is 10/30, which is 1/3. Okay, that's right. So when is sine of something equal to 1/3? So take the inverse sine of both sides. Inverse sine cancels out sine. So I get pi x over 10 equals inverse sine of 1/3. Now the hard part, like we talked about in class. What is this? Now you can plug into your calculator. You type in 1/3, go inverse sine, hit the button, right? But remember, that's only one of the solutions. That will give us this one. We need that point too, and that point is always pi minus the first solution that you got. Okay, so plus we have the plus pi n thing, okay? So already I did this wrong. Well, kind of. So I haven't taken the inverse sine yet, so we're okay, I guess, so far. Okay, now we have to do the two solutions. So let's do the principal solution first, of course. That's what your calculator spits out. So the principal solution. So we take what your calculator spits out, and I don't know what that is, so I'm going to have to get a calculator. So I type in 1/3 and make sure you have radian mode in. Got to have radian mode in. 1 divided by 3, I get 0.3, obviously it's 0.3333. I'm in radian mode. I take inverse sine, second sine, 0.339836. Okay, within like how many decimal places do you keep? I'm going to keep 0.33983. So 0.3398 is pretty good. So principal solution, we have pi x is over 10 is 0.3398. That's that. Plus, we know we could have 2 pi n's. We can get that answer plus 2 pi, or minus 2 pi, because keep going around the circle, right? We have that plus 2 pi, plus 2 pi, plus 2 pi, plus 2 pi. We have infinite number of, oh, sorry, actually it's this one, and then that one, and that one, and that one, forever. That's what this tells us. Now, after we add the 2 pi n, we solve for x. A lot of people do it first. They solve for x first, and then do 2 pi n, and then it's wrong. Because this pi and 10 is going to change our 2 pi here. So be really careful of that. Keep this stuff, and then only divide once we have the 2 pi n. Okay, so we have to multiply x, then we multiply by 10 over pi. So it's 10 over pi to get rid of that, right? Pi over 10 multiplied by 10 over pi to get rid of it, that's right. Times 0.3398 plus 10 over pi times 2 pi n. This is always nice, right? The pi's are going to cancel. So that will give us a pretty number. This is not a pretty number. So I'm just going to multiply that. So times 10 divided by pi. Don't even try to keep perfect numbers, okay? We're going to always do decimals here. 1.0817 is good enough. So x is equal to 1.0817 plus, okay, here we can keep perfect. The pi's cancel, 10 times 2 is 20 plus 20n. Well, obviously, keep that perfect. Okay, those are all the numbers where we get 280 for the first one. Now we got to get the symmetry solution, okay? So this is that solution. Now we got to get the symmetry solution. So we do the same thing, except now instead of this, it's pi minus that, okay? So let's see, I wrote this really big here. I'm going to copy it down over here small. So we have that the temperature is 30 sine of 2 pi x over 20 because we have 0 there, so let's write the x there, plus 270. Okay, so now let's do the symmetry solution. So the symmetry solution is, we have the same thing, we copy that down, pi x over 10 equals pi minus 0.3398. 3398 plus 2 pi n. Okay, the exact same thing, but it's always pi minus that one. And just because we should review, let's look at the unit circle. We're saying when does sine equal to 1/3? Sine is the y value, so 1/3, this is 1, so 1/3 is about right there. That's 1/3, so it's equal to 1/3 right here. And that would be 0.3398 radians. That's what the calculator gives you. But what the calculator doesn't give you is the one over here. And that one is pi minus, right here, this is by symmetry, that's also 0.3398. So it's pi minus that to give this angle. So that's what we're doing. The other one is pi minus it, plus we still have the 2 pi. We can run the circle again and again, or go around the circle backwards. It could be negative n. Okay, get the idea? Yeah. So I always like to do that to make sure, but once you've done that a lot, you just remember the symmetry solution is always pi minus what your calculator gives you. Okay, so then we do the same thing. X then is 10 over pi times that number. So what's pi minus 0.333398? Pi minus 0.3398 is 2.801. Oh, 2.801, that's practically 2.8. That's easy. 2.8 plus, again, same thing over here. This is always going to give you the same thing. So whatever you get here, 20n, we know we're going to get 20n down here too, so that's kind of nice. You just can check your work. It's this number that's going to be different. Okay, so finally we have x is 10, okay, what is that? Pi's, of course, there's no perfect math. So times 10 divided by pi. I get 8.918, let's say 8.92. So 8.92 plus, and again, this will be the same, 20n. All right, those are our points. Now, let's take the n equals 0 point, which will be this first one. The n equals 0 point is 8.92. Okay, so, and then always check your graph, okay? Check your graph. Does 8.92 make sense? Here's 10. So it makes sense this first green dot, yeah, it looks like about 8.9, about 9 there, right? It's a little bit before 10. So this is our 8.92. Okay, so this is at 8.92 minutes. So 8.92. And the first green dot looks like it's really close to 0. And that's when n equals 0 here, which is about at 1 minute, 1.0817. So it's at 1.0817. So the difference between those two is going to be that time difference. This one's at 1.0817 minutes. It gets to 280, stays there until down here. So all you got to do is subtract those numbers, and that will give us how long it's above 280 in each of these things. So that's pretty easy. So 8.92 minus 1.0817 is, just figure this out, minus 1.0817. I kept all the decimal places in my calculator so I can get a better answer than I wrote down. Oh, and it's terrible. 7.83668. Like, where do you round that off, right? 7.83668. Let's say, I didn't keep that many here. Let's say 7.84. I don't, probably should keep more than that, but since that number is only 2, yeah, 7.84 minutes. Wait, that makes no sense. Did I do that right? Wait, does that make sense? So this 8 minus 1 is 7. Oh, it does make sense. 8 minus 1 is 7.92 minus that is, okay, that makes sense. About 7.84 minutes. Let's write minutes here, so we're talking about. So that's 7.84 minutes. This one's 7.84 minutes. This one's 7.84 minutes. This one's 7.84 minutes. I guessed 8 earlier. Pretty good, huh? I'm pretty proud of myself. I was pretty close to right. Is that going to be 30? We got to get to 30. Or are we going to have to go to our next one? So let's multiply that by 4. That's 31. Okay, so 4 cycles is good enough because that gives us 31 minutes. However, this is the hard part. They say, how long will Gavin need to leave the cake in the oven? Somewhere before this cycle's up, it's going to get to 30 minutes, right? Because 4 times that, I just got 31.34, yeah, 31.346. Let's say 31.35. So the end of this cycle is 31.35 minutes. That's right there. Okay, this point here is 31.35 minutes. So we need 4 cycles. So we got to figure out now, where is that point? Looks like it's going to be between, this here is 70, halfway between is 70. So it's going to be somewhere right in there, right, where it hits 30 minutes. So about a minute before that, somewhere right in here, about 60 something minutes probably. Yeah, 60, because it hits here at 70, halfway down. We know it's going to be earlier than that dot, because that's 31.35 minutes above. So it's going to be somewhere in that point. So we're going to have to look for that point where it hits 30 minutes. When does that hit 30 minutes? Okay, so that hits 30 minutes. 31.35 minutes minus 30, or 1.35 minutes earlier than this point. Okay, so if we know that point, it's going to be, that's it. That point is 31.35 minutes above that. So we want to go 1.35 minutes earlier than that to get to 30. So this point minus 1.35. See the logic there? So minus 1.35. So what is that point? Well, that is the symmetry solution point. This is the n equals 0 symmetry solution point, right? Because that's the 1. That's the n equals 0 principal solution point. And this is the n equals 0 symmetry solution point. So that's n equals 0. This one's n equal 1. This is the n equal 2. And this is the n equal 3. So we want 1.35 minutes before the n equals 3 symmetry point. Okay, that's what we have to look for. So where is that? But we have a formula for that. This is a symmetry solution when n equals 3. That's what that point is there. We know it's going to be a little less than 70. We better get like 68 or something. So let's try it out. This is 8.92 plus n equals 3. Oh, that's easy math. That's just plus 60, which is 68.92 minutes. So that point there, that symmetry point is 68.92 minutes. We want to be a minute 35 earlier than that. So finally, the last step I have to do here is go 68.92 minus 1.35, because that's to get to 30 minutes, right? Because right there is at 31.35 minutes. And then we're done. Then we're solved the problem, and it only took me 24 minutes, a little over 24 minutes. Okay, so 68.92 minus 1.35. I get 67.57. So 67.57 minutes. So he has to have it in the oven for 67.57 minutes. That is that point right there where it hits 30 minutes, 67.57. And then you can take it out because at that point it was above 280 degrees for 30 minutes. 7.84, 7.84, 7.84, and then 7.84 minus the 1.35. That would have been too long, and he would have burned his, whatever was his, been making scones or something. Yeah, so we don't want that to happen. Phew! Okay, look at that full of stuff. So that's the logic. Drawing a good picture really helps. Okay, it just absolutely helps. Writing out the equation in the beginning, figuring out this thing here, right? Figuring out the phase, which was 0, which is nice. We didn't have to worry about the phase, but it's not that much harder if you got to figure out where the sine wave is the middle going up. And then thinking about what's actually happening, you know, drawing these lines in there and figuring out those things, doing the symmetry and principal solutions very carefully, showing all your steps, you know, making sure you add the 2 pi in before you solve for x here. If we had had like a phase, we would have had an x plus 3 or something, and then you subtract the 3 first, then you multiply by pi over n. We didn't have to do that, so a little more algebra if we'd had that. Yeah, these are a lot of work, and there will be one. This is like a classic problem that could be on your final, okay, where you got to draw the picture, figure out the thing, figure out how long it's going to be. You know, kind of like chapter 19 plus a bunch of extra steps because we have the symmetry solutions and really looking at the logic of the whole picture. So, good problem. Yeah, let's see the whole thing. Awesome. Okay, anyway, I really hope you followed that. And hopefully by looking at how we did this one, you can figure out how to do a bunch of the other ones. And then and we can maybe go around, maybe make another video or something. But this is the gist of it. If you can do these, you're doing pretty good. So, all right, good. Thanks for holding on this long. I will see you later.